Hello again, everybody, and welcome to another Geo-Institute live stream as part of our Summer of Live 2024. Today, we celebrate the 150th birthday of the Journal of Geotechnical and Geoenvironmental Engineering, which you may know and love as JGGE. My name is Brad Keeler. I'm the director of the Geo-Institute. Thanks for being with us this afternoon for this little party that we're going to have in honor of our flagship journal. If you don't know anything about the Geo-Institute, as I always say, after you watch this today, you can head over to geoinstitute.org, and there you will find out more things than your brain can handle about us, such as that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and/or geologists, and that we are part of the American Society of Civil Engineers. If you like what you see today, and I think you're going to, we've put together a good one for you here. Click like, subscribe, and get notifications, and we will, of course, lovingly let you know every time we post something to the YouTube channel. As I mentioned, today is a very special birthday celebration, and so we have brought out all the all-stars today. Before we get kicked off with our panel, we are going to have a few words from the Managing Director of Publications at ASCE. It is Dana Compton. She will wish us well as we go into this panel.
Thanks, Brad. Thanks for inviting me today. So, as Brad mentioned, I am publisher at ASCE. And as you probably saw in the promo for this session, we are very proud that we have 15 of ASCE's flagship journals celebrating this milestone this year of publication of it, the 150th volume of the journal. So we're incredibly excited about this in publications, very happy that JGGE and the Geo-Institute are as excited about this as we are. We pride ourselves on being the largest publisher of civil engineering content, and JGGE is one of our most important flagship journals. So I'm really delighted to be here, happy that you're all celebrating. This is a real achievement. And I will turn it over to our current editor-in-chief, Catherine O'Sullivan. Thank you so much.
Thanks, Dana. So this milestone of getting to the 150th volume of our journal gives us an opportunity to reflect on and to articulate the achievements of the geotechnical engineering community in developing and curating this journal over a very long period of time. And so to recognize that and allow that conversation to take place, we had a special session at the Geo-Congress in March. And the quality of the contributions from the 5 speakers who spoke at that session was such that we thought this needs to be disseminated to the broader geotechnical engineering community, both within the US and internationally. And so the speakers kindly agreed to repeating their performance from the Geo-Congress and giving these presentations again today. And it was an enormous amount of work on behalf of the speakers in terms of collating and reviewing papers in the journal and synthesizing that into what I think you will see are very, very nice presentations. So I'm going to introduce all of the speakers now, and then they're going to speak like a relay team and pass from one to the other. And the first person to speak will be Rod Salgado, who is the Charles Pankow Professor of Civil Engineering at Purdue University. He is the former editor-in-chief of the journal, chair of the Geo-Institute Technical Publications Committee, and he's going to talk about contributions to foundations engineering. Rod will pass it over to Rudy Bonaparte, who's a chairman of Geosyntec Consultants and a professor of practice at Georgia Tech. And he's going to give a review of contributions to geoenvironmental engineering in the journal. And Rudy will hand the baton over to Thalia Traversaro, who is a regional technical director with Fugro in North America and an associate editor of the journal. And Thalia will talk about contributions to geotechnical earthquake engineering. After Thalia, Anand Popala, who is the AP and Florence Wiley Chair and this in the Center for Infrastructure Renewal at Texas A&M University, who's also an associate editor of the JGGE, we'll talk about contributions to soil behavior and characterization. And finally, Gabr, who's our editor-at-large, a former editor-in-chief of the journal, and a distinguished professor of civil engineering and construction in North Carolina State University, will give a review of the history of the journal. So I hope you all enjoy the presentations as much as I did when I had that preview in March. And thank you for joining. The final thing I would like to say is we'd welcome contributions from the audience, and you can add your comments and questions in the live stream chat. So I'm now going to pass to Rod.
Thank you, Catherine, and thank you, Catherine, and the whole GI and ASCE staff for organizing this. So I hope that everybody's seeing my PowerPoint now. So what I was asked to do was go over the contributions made to the journal on the general topic of foundation engineering. And we presented this in person in February in the Geo-Congress, and we are repeating that here. So what I'm going to be talking about is papers submitted to the journal and published in the journal on foundation engineering that influenced the profession and also my own work. So we'll be discussing some of the key lessons from these papers and how the lessons withstood the test of time. So in this connection, the papers are not necessarily the best science available today, and some you might even say are not perhaps good science, but they got work underway that became really important to the profession. I'll talk a little bit about citation data, or at least I'll have the numbers on the slides for the JGGE papers only. In selecting the papers to include here, I considered foundation engineering. I consider a narrow definition of foundation engineering. So basically, the focus is on papers that explicitly dealt with foundation elements, piles, footings, etc., in which some significant vertical load was present. So no papers on slopes, retaining structures, seismicity, and so on are included. So we'll start with shallow foundations. With this paper, actually a discussion by Meyerhoff of this paper by Jumi Keys, published in 1956. So this was a discussion based on experimental work that Meyerhoff had been doing, and it's apparently the first time that we get into bearing capacity equation factors for load eccentricity and inclination. The other interesting piece of this discussion was Meyerhoff's observation that in his experiments, the shape of the slip surfaces looked like a log spiral. So how has that withstood the test of time, as we said we would talk about? So what have we learned about those two things since? We know, for example, that there is fundamental error in the bearing capacity equation for sand. An important part of that is that sand does not follow an associated flow rule, which was a key assumption in the derivation of the bearing capacity equation originally. This leads to an over-prediction of the bearing capacity of footings. In sand, if you use the original unmodified versions of the bearing capacity equation, Eccentricity is still accounted for in the same manner if you're working with the bearing capacity equation, but there are alternative approaches like VHM diagrams. Imaging plus digital image correlation analysis of these images do show that the surfaces resemble a log spiral, but they are not really a log spiral, even because you don't have a constant friction angle along the entire shear band or line. Two important contributions that appeared in the journal were from Rich Eismer and Richard, dealing with foundation vibrations. And the idea here was basically the application of analysis for single degree of freedom systems to foundation vibrations. In the paper or papers, there was discussion of different modes of vibration, 3 rotations and 3 translation modes. There was a recognition of the effect of nonlinearities on the response of the foundations. And there was discussion of design, such as a possible strategy of not crossing the natural frequency of the systems during design. An important result of this work was the proposal of what is today known as the Leismer analog, which essentially converts energy loss due to wave propagation to a representation using a dashpot and viscosity. Moving on to deep foundations, starting with axial resistance. This paper by Meyerhoff in 1956 followed a trend at that time of trying to approach the calculation of the base capacity of piles using something resembling the bearing capacity equation. This particular proposal by Meyerhoff, of course, was not correct. You can see that the mechanism that was proposed for failure of the pile was kinematically inadmissible. And today we're largely beyond using this type of approach for pile axial resistance calculation. For example, as we can see in this video, that those velocities don't really turn around and come back to towards the pile as Meyerhoff had envisioned, but you're actually looking at velocities that tend to horizontal, right? So the pile or cone penetrometer is pushing the soil away from it in a horizontal or lateral direction. We have also learned that it's much more effective to try to do pile-based resistance calculations using something like the CPT. So you're basically analogizing the limit bearing capacity of a pile to the cone resistance, and then you're expressing pile-based resistance, pile unit-based resistance at different levels of settlement to QC. So you're expressing it as some fraction of QC. The journal also published important papers dealing with open-ended piles. So this paper by Randolph et al., for example, published in 1992, attempted perhaps the first or one of the first analyses of the mechanics of plug formation in an open-ended pile. That work continued at the University of Western Australia, and Lehane and Randolph published this other paper in which they basically concluded that the unit-based resistance of open-ended piles and in particular the soil plug could be analogized to that of a bored or non-displacement pile, or at least it could be calculated using the unit-based resistance of open-ended piles as a reference. So what have we learned since? We have learned that plug formation is a function of a number of variables. Relative density is an important one. The presence of layering, whether the pile is going from loose or soft soil into dense or steep soil, or the opposite. That makes a significant difference in whether you form a plug or not. The effective stress state, the diameter of the pile. It's of course easier to plug if you have a smaller diameter, and wall thickness. Something else that has been learned is that even if you have a fully coring installation, that plug is still active. So it becomes then a matter of calculating what the contribution of the plug is to base resistance. Another important paper published in the journal had to do with the difference in shaft capacity of the pile between tension and compression. This is a paper by Nicole and Randolph, published in 1993. And the paper brought attention to the difference that can exist between tensile and compressive shaft capacity. The authors at that time hypothesized that this would be due to Poisson's effect. I think today we know that not to be the case. For example, in this pair of tests, we're looking at pre-installed, so something that resembles a non-displacement pile on the left and a displacement pile on the right. And you can see that there is a significant difference in unit shaft resistance for the displacement pile, but that the shaft resistance for non-displacement pile is the same whether you are pulling the pile up or pushing it down. And the explanation for that is that when you install the pile, by pushing it down or driving it down, you are realigning the fabric of the soil in a way that makes the soil stiffer to further downward loading. But the fabric is not that stiff for a tensile loading. So the reason then for the difference really is the impact of installation on the fabric reorientation in the soil. Lehane, Jardine, Bond, and Frank published in the journal this very important contribution. They used a model pile that allowed them to track the shaft resistance as the pile was driven down into the ground. And what was seen is that the shaft resistance tended to degrade the most for locations up the pile, further away from the pile tip. And we know today that what's going on here is that if the soil next to the pile has experienced a larger number of cycles of vibration because of contractancy of the soil during vibration, during load cycling, that soil would have had a tendency to contract. Since contraction doesn't really happen around the pile in a global sense, what you see instead is a reduction in the normal effective stress on the pile, and that in turn leads to lower shaft resistance. So this has become known as shaft resistance degradation. It's something that modern methods of pile design include, and it was a very important contribution. Another very impactful contribution was published in the journal in 1988. This paper by Harry Poulos, proposing the use of cyclic stability diagrams for axially loaded pile design. This is something that is still used a lot in the offshore industry. And the idea here is that depending on the number of load cycles and the amplitude of the load cycles, you may see a significant degradation of axial capacity and possibly even a loss of stability, or you may not see that at all. So it all depends on the combination between load, amplitude, a number of vibrations. So these diagrams are a part of design to this day. Moving on to pile driving. Perhaps the most impactful paper in this area is the paper by E.A.L. Smith, proposing what we know today as the wave equation analysis to try to simulate the driving of piles in the ground. And what you do here is you start with known or assumed static resistance along the shaft of the pile and at the base, and using that using information about energy loss along the pile shaft, so damping, you try to simulate the driving of the pile. Basically, you try to simulate how much a pile will advance for a given hammer blow if you know or knowing the static resistance of the pile and the damping characteristics of the soil. An interesting fact or a fun fact about this paper is that if you look at the initials of the author, E.A.L., there are key variables in this analysis. So E is Young's modulus, A is the pile cross-sectional area, L is the pile length, and you could argue that the S in Smith stands for settlement, perhaps. Kind of the reverse of that, in logical, kind of reverse logic of that paper is instead of going from non-static resistance to driving resistance, you try to go from driving resistance to static resistance. And that's what this contribution by Rausch, Goebel, and Likings is all about. And it became the basis for methods of quality assurance that we use in our quality control that we use in geotechnical engineering today to a large extent, which are dynamic load tests. And so again, the idea here is that you measure force and velocity during a hammer blow, and you try to figure out what that tells you about the static resistance of the pile. So the methods that allow you to do this are known as signal matching methods. So what we have learned since is that the relatively simple models used originally by Rausch et al. Can lead to under-prediction of pile capacity. And so if you use more realistic models for the soil and for the pile-soil interaction, you can get more accurate estimations of pile capacity. But the method in its core, as originally proposed, stands to this day. Moving on to lateral loading, it appears that the first time that something that we would now recognize as the PY method was proposed in the paper by McClellan and Falk in 1956. And so the key recognition here by the authors was that the normal stress between the pile and the soil would depend on the lateral deflection Y in a nonlinear manner. And so this, of course, would lead to so-called PY curves in which you don't have a linear relationship between P and Y, but a nonlinear one. What we have learned since is that there is an alternative route, which is not often used in practice, but probably leads to more accurate results, which is to do analysis based on the soil model as a continuum. So you can, of course, use FEM, but there are alternatives to FEM that produce faster results. They are just as accurate. I believe the final paper that I have included in this presentation is this paper by Stewart and co-authors, which was recently published in the journal. It deals with the case history of the settlement and the tilt of the Millennium Tower in San Francisco. And the authors go into great detail into aspects of what happened, including aspects involving drainage issues. However, I think an important lesson from this case history that I hope the journal revisits with more publications is the risk of placing deep foundations on intermediate layers. If you do that, you need robust analysis to go with it to make sure that that layer will be able to carry the load that you're placing on it. This is not a new problem. If you go around the world, you will find similar cases. For example, in the city of Santos in Brazil, you also have buildings that were placed on deep foundations in intermediate layers that have settled and have tilted. So it's definitely one of those papers, one of those areas that the journal tends to publish a lot, which is case histories that offer the community an opportunity to reflect on these challenges. All right, so I think I have shared with you a number of papers that illustrate the importance of the JGGE in advancing the knowledge of foundation engineering over the years. There have been seminal contributions to the journal in terms of shallow foundation bearing capacity, foundation vibrations, the axial capacity of piles, non-displacement, displacement, and open-ended pipe piles. The key papers that laid out the dynamic load test method of foundation verification and wave equation analysis for foundation design and planning, they were published in the journal. The PY method, which is widely used in practice, the original paper was published in the journal. So I think that these papers illustrate the importance of the journal to the community. Thank you very much again for the initiative of organizing this, and I'll pass this on to Rudy now.
Thank you, Rod. I'll just get a touch organized here. My topic today is geoenvironmental engineering contributions to the ASCE JGGE. To prepare for today, I conducted a survey of the journal to identify geoenvironmental papers. I estimate that as of this time, there have been about 240 such papers in the journal. The first paper was authored in 1965 by Jim Mitchell and his students on the topic of the permeability of compacted clays. In the 1970s, I identified two papers related to geoenvironmental engineering, one on MSW landfill rates and another on the methane migration around MSW landfills. Moving on to the 1980s, there were about 10 papers on a broader range of topics. And then in the 1990s, about 25 papers on an even broader range of topics. And you can see the trend here. In the 2000s, 60 papers, 2010s, 90 papers. And we're tracking for the 2020s at about 100 papers on a continually increasing range of topics. In addition to there we go. In addition to the papers in the journal, there have been several hundred geoenvironmental papers published in the proceedings of ASCE GI conferences, such as the one shown here. But for today's talk, we're only going to focus on papers that appeared in the journal. When we think about geoenvironmental engineering, It includes all of the topics shown here. It's a broad field encompassing a lot of things. For today, we're just going to touch on the first three on the left-hand side of this slide: waste containment systems, waste mass stability, and landfill performance. These are the three that have received the most attention in the journal over the years. So let's start with a few notable papers on compacted clay liners. As I already mentioned, the first journal paper from 1965 was authored by Jim Mitchell and several of his students, titled Permeability of Compacted Clay. The paper identified for the first time the importance of compacting wet of the line of optimums using kneading and not static compaction to achieve low permeability. And this is shown in the figures from the paper on this slide. This paper was the starting point for much future work by others that appeared in the journal. For example, nearly two decades later, Dave Daniel launched a major research program studying the factors controlling the hydraulic conductivity of clay liners. His 1984 paper, Predicting Hydraulic Conductivity of Clay Liners, showed the important role that compaction moisture content has on clay liner permeability, as shown on the figure from the paper on the left-hand side of the slide. A little later, in 1990, Dave and his student Craig Benson authored an important paper clearly defining the compaction water content and dry density conditions needed to achieve low hydraulic conductivity. These conditions are illustrated in the figure from the paper on the right-hand side. Two more important papers on compacted clay liners are shown here. In another 1990 paper, Benson and Daniel described the problem of trying to achieve low hydraulic conductivity when the clay material contains large clods. And if you work in this area, you know that's a fairly common occurrence. They showed that to achieve low hydraulic conductivity, the combination of compaction, water content, and compaction energy had to be sufficient to destroy the clods and eliminate large interclod voids. This is clearly illustrated in the photo on the left, where you see at the left, for compaction at 12% moisture content and standard Proctor energy, the clods were not destroyed, whereas at 16% moisture and modified Proctor compaction, you have a homogeneous clay liner material. In 1999, Benson, Daniel, and Boutwell synthesized data for 85 full-scale clay liners for which field permeability testing existed, such as from sealed double-ring infiltrometers. And they provided comprehensive recommendations for constructing high-quality clay liners in the field. Their recommendations, shown in the figure on the right, are still in use today. Let's move on now to highlight just a few noteworthy papers on the topic of geosynthetic, and soil geosynthetic interface strength. And for those of you that work in these areas, you know that this is very important with respect to the landfill of any geosynthetic line facility. The first journal paper to tackle this topic was in 1990. In the paper, Jim Mitchell and Ray and Harry Seed reported on their forensic investigation of the 1988 Kettleman Hills landfill failure in California. The results are shown in the left-hand side of this slide. They conducted a lot of interface testing and identified very low residual interface strengths, as low as 8 degrees, mobilized in some cases with just a few millimeters of displacement. These results demonstrated for the first time the potential for progressive shear failure of geosynthetic mined landfills. A few years later, Tim Stark and his student, Alan Popple, developed a torsional ring shear testing procedure to evaluate the residual strengths of soil and geosynthetic interfaces. Some of these results are shown on the right. These results further elucidated the strain softening nature of geosynthetic interfaces and brought further attention for the potential for progressive failure at geosynthetic lined landfills. In the latter 1990s, Dave Daniel, Bob Kerner, and I, as principal investigators for EPA, designed, constructed, instrumented, and monitored 14 geosynthetic clay liner, or GCL, final cover systems. Several of the plots were designed to fail and did, as shown in the photograph. Others remained stable with varying magnitudes of shear displacements. The test plots yielded a great deal of useful information that was interpreted to better understand the interface and internal shear strength of GCLs and their proper use in landfill cover systems. I'll move on now to highlight just a few noteworthy papers on the topic of landfill slope stability. I've already mentioned the 1988 failure of the Kettleman Hills landfill, shown in the photo here, and the paper on interface shear testing by Jim Mitchell and Aaron and Ray Seed. These authors had a second journal paper on this failure that used the interface test results and slope stability analyses to identify the landfill failure mechanism. At the time of publication, this was by far the most comprehensive and important paper in the literature evaluating the causes of a major landfill failure. Additional journal contributions that studied the Kettleman Hills landfill failure include a 1998 paper by Bob Gilbert et al., shown in the upper left, and a 2001 paper by George Phils et al., shown in the lower left. Tim Stark and his colleagues studied the 1996 Rumpke landfill failure in Ohio, a very large failure that you can see in the photograph on this slide. They presented their study results in two journal papers shown here. Important lessons learned for this case study include the risks of allowing leachate levels to build up in old unlined landfills, the risks of overfilling old unlined landfills beyond their permitted grades, and the risk of progressive softening and strength loss of native foundation soils. In this 2020 journal paper, with my co-authors, I present the written version of my 2018 Terzaghi lecture, Geotechnical Stability of Waste Fills, Lessons Learned, and Continuing Challenges. This paper starts by reviewing several historical landfill failures and their root causes. It then focuses on previously unpublished landfill failures of the past decade, describing the root causes for these more modern failures, which are different than the causes for the older failures. The paper finishes by describing how such failures can be prevented in the future. And any time you conduct a stability analysis of a waste mass, you need to select shear strength parameters for the waste. We don't routinely conduct waste strength testing for projects. It's too complex and expensive. You need very large samples. It's very hard to make them homogeneous and consistent. You have environmental issues because it's a waste material. Instead, we mostly rely on the results of published studies, such as the four shown here, that appeared in the journal between 2007 and 2013 by Mo Gabr, Jonathan Bray, Chris Barreither, and Ed Kavazanjian, and all their colleagues listed on the papers. Another topic that has been covered in the journal is the performance of geomembrane liners. One of the most important parameters for geomembranes is service life. That is, how long will the geomembrane last? The first paper in the journal on this topic was in 1993 by Gray Swan, Bob Kerner, and Art Lord. The paper presented a new test for evaluating the stress cracking resistance of HDPE geomembranes and related the test results to the service life of those materials. Test results are shown in the figure on the left. As a result of their work, the manufacturers of these geomembranes developed new polymer formulations that greatly increased geomembrane stress crack resistance and service life. Two other important papers are shown here, authored by Kerry Rowe and his colleagues at Queen's University. One in 2008 on antioxidant depletion in geomembranes, also very important for predicting the service life of these materials, and another in 2012 on issues associated with the thermal expansion and contraction of geomembranes. One final important paper related to geomembrane performance is Kerry Rowe's 2017 Terzaghi lecture, Protecting the Environment with Geosynthetics. The paper summarizes and organizes an enormous amount of work conducted by Kerry his colleagues, and others. The paper touches on topics such as the causes, sizes, and frequency of holes in installed geomembranes, leakage rates through geomembranes and composite liners, performance of leachate collection systems, and antioxidant depletion and the service life of geomembranes. It's an excellent paper and I highly recommend it. I'll finish my talk with 2 slides on geosynthetic clay liners, or GCLs. Over the years, the journal has had many important contributions on this topic. David Daniel and his students were the first to present journal research on these materials. In a 1996 paper, they looked at the rehydration of GCLs after desiccation and found that these materials effectively rehydrated when wet, an important property. And this is shown by the reduction in hydraulic conductivity in the plot on the left-hand side of the slide. In a 1997 paper, they evaluated the effects of various chemical permeants on GCL hydraulic conductivity, showing increases in hydraulic conductivity when the GCL was permeated with leachate rich in divalent cations, primarily calcium, which replaced the sodium cations in the GCL, causing bentonite shrinkage. Not long after Daniel's work, Craig Benson and his students and colleagues began their work on GCLs. The work spanned more than 2 decades, and it continues today. I'll highlight just 2 papers from this group. The first, from 2004, showed the effects of permeant ionic strength and the ratio of monovalent to divalent cations, called the RMD, on GCL hydraulic conductivity. And we can see that in the graphic on the left-hand side, and you see the RMD and the ionic strength and the correlation developed. The second paper, from 2007, looked at the performance of GCLs in a full-scale final cover system, finding increases in GCL hydraulic conductivity over time due to both cation exchange reactions and dehydration. And you can see the effects primarily of dehydration in the photograph. I'll wrap up by simply making the point that many have contributed geo-environmental content to the journal, and that the journal has been a leader in this regard. If I had more time, there are many more contributions I would like to recognize from the people shown here and from many others. The journal has been an extremely important role in establishing and advancing the geo-environmental field. I congratulate ASCE on 150 years of success with the journal, and I look forward to seeing the contributions that will be made in the coming years. With that, I'll stop sharing my screen, and I will turn the floor over to Thalia. Thalia?
Let me share my screen. So thank you, Rudy, and good afternoon, good evening, everyone, wherever you may be. I will be presenting on the topic of geotechnical earthquake engineering, and in reading papers, rereading, and preparing this presentation, I very much reflected on how papers that have been published in this journal helped shape a practitioner like myself. And so this is to offer some background on my perspective. As an undergraduate, I performed research in soil dynamics at the National Technical University of Athens in Greece, continued with my PhD research in strong ground motions and slope stability at UC Berkeley. And for the past 20 years or so, I have been practicing geotechnical engineering with a focus on infrastructure design to withstand earthquake-related hazards. So let's dive right into it. Knowledge in the field of geotechnical earthquake engineering appears to advance in leaps when strong earthquakes happen. And this is from the time capsule report by TC203, illustrating the evolution of the field in relation to the occurrence of significant earthquakes. And the field was essentially established back in the 60s following the devastating earthquakes in Chile first, Alaska, Japan, which brought to our attention the importance of geotechnical hazards, especially with respect to the performance of structures and the loss of life. So looking now at the evolution of the field from the 60s to present, we can broadly subdivide into three periods. 60s and 70s was the period of raising awareness. The 80s and 90s, the period of developing early models and methodologies to assess earthquake effects. And for the past 2 decades, the focus has been, on one hand, on refining the early models and methodologies, and on the other, on developing advanced models and exploring special cases. And I will be using a similar timeline to look at key papers published in ASCE for this presentation. And so I chose to focus on 4 main topics that represent the majority of research and practice. And these are liquefaction, dynamic site response and local site effects, seismic analysis and design of earth and retaining structures, and seismic foundation design and soil structure interaction. And we will note that in early publications, these topics were addressed almost independently of each other. Whereas as the field evolves, interconnections between these topics are also addressed in research. And there are also areas that I'm referring to as enablers. So for example, the characterization of dynamic soil behavior, availability of case studies and physical model tests, advancements in numerical modeling and probabilistic methods. And we see that progress in these areas triggers significant advancements in the 4 main topics. So in terms of identifying key papers for this presentation, I prepared a set of criteria listed here for completeness. And for the remaining of the presentation, I plan to present 2 slides per each topic. The first will show the timeline of the evolution of the topic, along with some dominant questions that preoccupied the profession. And then the second will follow with 3 to 5 publications selected based on this criteria that I think are worthwhile reading if you want to follow the progress of the specific topic. So starting with the first topic, which is the dynamic site response and local site effects. Back in the 50s, or earthquakes that happened back in the 50s and 60s, highlighted the significant influence of local soil conditions on surface ground motions. And initially, local site effects were addressed mostly qualitatively. However, it very quickly became apparent that quantitative assessments were needed. And this is when the first analysis tools were proposed based on simplified, that is, equivalent linear, mostly constitutive models. As the field matured in the 80s, new questions raised were around amplification of weak motions by soft soils, soil nonlinearity in general, topographic effects for dams, but also research focused on the characterization of dynamic soil properties for use in site response analysis. Then in the early 2000s, refined tools for site response analysis were developed, incorporating soil nonlinearity, also enabling analysis in 2 dimensions, and calibration and validations of these tools was mostly enabled by comparisons to downhole array recordings. Some new issues that emerged include near-fault motions, also statistical approaches for site response analysis. And in the past 15 years, research and practice moved mostly towards analysis in multiple dimensions, incorporating the effects of spatial variability in soil properties, also soil liquefaction through effective stress approaches. And finally, newer topics include non-ergodic and synthetic ground motions. So in terms of some key papers, in 1986, Robertson and co-workers introduced a new test, the seismic CPT, to measure shear velocity in situ. And this was or is a cost and time efficient test that has been used by practicing engineers ever since. Next, we have a set of 2 papers on the geovergy max and damping curves. The paper by Seed and co-workers focuses on the cohesionless soils, and it includes an excellent discussion on the factors influencing geovergy max and damping. And similarly, Vucetich and Dobry, they highlighted the important effect of plasticity for cohesive soils, and they proposed a set of curves. And all the curves presented in these papers are still are used to this date, with some refinements, of course, by later research. In 2016, Groholski and co-authors presented a simplified constitutive model for site response analysis, which meets the requirement of limiting shear stress at large shear strains. And this model has been incorporated in software widely used in practice. And finally, more recently, Halal and co-authors, they compared the state-of-the-art approaches to account spatial variability in one-dimensional site response analysis, which is not commonly done in practice. They use geophysical H/V measurements to inform the degree of spatial variability and provided insights and practical guidance. So the second topic is that of seismic analysis and design of earthen retaining structures. And in the early days, research was motivated by the need to design dams for seismic actions. And this is when tools like the pseudostatic analysis or the concept of the seismic coefficient were first introduced. Also, the rigid block model, which was presented in a seminal paper by Newmark, was proposed as a simple tool to approximate seismic slope displacement. Then there was a clear evolution from force-based methods towards displacement-based methods. And this is when the first simplified procedures were proposed to quantify seismic slope displacements. Also, the importance of slope flexibility was highlighted by researchers. But in general, these simplified procedures were mostly decoupled in the treatment of wave propagation and slope sliding. Then in the 1990s, there were improvements in the state of practice that were triggered primarily by the new federal regulations for the seismic design of solid weight landfills. And this is when refined slope models were presented that coupled wave propagation and sliding. And subsequently, improved simplified procedures were developed based on these refined models, and also probabilistic approaches were proposed. And then more recently, research has focused on further refinements of simplified procedures based on larger data sets and different environments, but also on the development of soil constitutive models, allowing us to perform more detailed coupled nonlinear deformation analysis. In terms of key papers, McDeasy and Seed's simplified procedure for earthquake-induced deformations is the first such method which offered a simple yet rational approach for seismic design of dams and embankments, and this has been used by practicing engineers for many decades since its publications. Then Kramer and Smith and separately Rathje and Bray proposed improved couple models, also accounting for slope flexibility, and this became the basis for enhanced simplified procedures. So then, building on these models, Bray and Travasaru proposed a simplified procedure which was formulated in a way that it would for the first time allow a probabilistic assessment of seismic slope displacements and associated displacement hazard. The last paper here is by Alatic and Sitar for retaining walls. And the authors, based on a combination of centrifuge experiments and numerical studies, they demonstrated that the state of practice for the design of cantilever retaining structures is conservative, and they proposed practical decision rules. The third topic is huge, that of soil liquefaction. So after the devastating earthquakes in Alaska and Niigata in Japan, geotechnical engineers took serious interest in this phenomenon. And the next decade, the first simplified procedures to evaluate liquefaction potential were presented. And those were later refined based on larger data sets, also alternative formulations and parameters and intensity measures. But more importantly, the profession started exploring the effects of soil liquefaction rather than just focusing on liquefaction triggering. And also the concept of residual strength was proposed to characterize properties of liquefied ground in quantitative evaluations of liquefaction effects. And in the early 2000s, a number of probabilistic methods were also presented, but also liquefaction of intermediate soils was studied in the aftermath of the Kocaeli earthquake in Turkey. In the last 10 years, the profession shifted towards performance-based design, and this has been enabled by significant advancements in soil constitutive modeling, numerical modeling platforms and tools, and complex experimental work. We also see that the effects of spatial variability in liquefaction-induced demands are studied in more detail, and at the same time, liquefaction and its effects is studied for a wider range of soils. And finally, researchers are also evaluating more innovative approaches to mitigate liquefaction hazards. So in terms of key publications in this topic, SEEDS, a state-of-the-art paper on soil liquefaction and cyclic mobility for level ground earthquakes, summarizes the profession's state of knowledge in the 70s. And in addition to proposing the first empirical approach, it makes an important distinction between flow liquefaction and cyclic mobility. Then Kokusho's experimental work was instrumental really in highlighting the possible effects of pore water redistribution, resulting in water filming beneath low permeability layers and triggering potentially post-shaking instability under gravity loads. Then, as part of research focusing on liquefaction of silty soils, Brain, Sansio ran a large number of laboratory tests, and they recommended that the Chinese criteria should be discontinued for the assessment of liquefaction susceptibility of intermediate soils. At that same time, Boulanger and Idris recommended to differentiate between sand-like and clay-like behavior. And I do find this concept very insightful. It has helped me certainly engage with non-technical audiences, such as our clients are mostly. And last but not least, following observations during earthquakes in New Zealand, Maurer and his co-authors found that LPI can overpredict liquefaction potential for interbedded soils and soils with high fines content, and they proposed changes in the calculation to achieve better predictions. So the last topic is that of seismic foundation design and soil structure interaction. And in the early days, research focused on shallow or embedded foundations. This was motivated by problems related to machine vibrations and seismic design of nuclear power plants. This is when simplified analogs were developed for computing foundation impedances, mostly treating soil as homogeneous half space, and when early finite element computer programs were developed based, again, on simple constitutive models, mostly equivalent linear. Then in the 1980s and 90s, there were new challenges related to seismic design of deep foundations and foundations in layered soils. And at the same time, there was a larger number of earthquake recordings and an increase in experimental work, and this allowed better calibration and validation of simple design tools to incorporate soil structure interaction effects. And in the last 20 years, profession or researchers started working on increasingly complex problems, also involving soil liquefaction. And as I pointed out earlier, the profession transitioned towards seismic design based on performance rather, and developing and presenting tools to do that more reliably. In terms of some key publications, in 1975, Seed and co-authors reviewed the strengths and limitations of the state-of-the-art at the time to evaluate soil structure interaction. And they stated that this seismic soil structure interaction is an extremely complex problem, and it is necessary to adopt methods that have the capability to incorporate many and hopefully the most important aspects of the actual conditions. And I think this statement all around employing engineering judgment, even in the selection of our tools, setting up to perform evaluations, remains true even today, even with the significant advancements in this field. Then the paper by Gazetas presented here a comprehensive set of dynamic foundation impedances, which could be used by practicing engineers, and due to its simplicity, is a practical tool allowing parametric analysis to develop insights. Boulanger and his co-authors present a series of centrifuge experiments to demonstrate the validity of the dynamic PY analysis for pile-supported structures in soft ground. And in the same year, Stewart and his co-authors presented methods for the treatment of kinematic and inertial soil structure interaction effects in buildings based on a large database of recordings from earthquakes, mostly in California. And finally, Gadjan and Qatar presented a series of centrifuge experiments which provided support to the novel concept of allowing the soil to yield in place to improve the performance of the structure during seismic loading. I have added here this extra slide for soil structure interaction in the presence of liquefaction due to the significance of the topic. And first, with a series of experiments, Brandenburg and co-authors, they characterized the soil pile interaction in liquefiable ground with lateral spreading, and they provided much needed insights on loading patterns. Then Dashti and her co-authors ran a series of centrifuge experiments which improved our understanding on the dominant settlement mechanisms for building with shallow foundations on liquefiable soils. And one very useful conclusion from that paper is that, contrary to the state of practice at the time, liquefaction-induced building settlement is not proportional to the thickness of the liquefiable layer. And finally, Sina and his co-authors proposed a novel displacement-based method to assess liquefaction-induced downdrag, which is typically treated with force-based methods still in practice, unfortunately. So with that, what should we anticipate looking forward? There are additional enablers to boost further advancements in the field of geotechnical earthquake engineering, tremendous increase in computational power, artificial intelligence, of course, new challenging design problems, new materials, and the journal is already promoting publications in these areas. And I'm sure that as in the past, also in the future, it will continue to play an instrumental role in shaping the field of geotechnical earthquake engineering. Before I finish, I would like to take the opportunity to thank here Professor Marina Padazidou for bringing to my attention the TC203 time capsule report and initiative. Also Professor O'Sullivan for her leadership in organizing this session, and Brad and the Geo-Institute for making it all happen. And also you for your time and attention. And with that, I'll hand it off to Professor Pupala.
Thank you, Toria. I'm going to start. My presentation is going to be focusing on contributions to soil behavior and characterization. So I just want to give you an overview of what I'll be covering. These two topics itself probably deserve 15 minutes each, but when I combine everything into 15 minutes, that probably going to miss some important great works. If that happens, please accept my apologies. The way we cover it on the left-hand side, soil behavior, I'll focus on soil fabric issues and shear banding. And I also want to cover a little bit about ground improvement, starting with cementitious stabilizers and some polymeric stabilizers. And then I'll end with biogeotechniques. On the right-hand side, we have in situ soil characterization methods, and also talk about some problematic soils like swelling soils, erodible soils. And there's an area which is overlapping between both of them is unsaturated soils and some topics like sulfate-induced heaving. It actually requires both understanding of behavior and also characterization. So most of the papers that I present here are all JGGE papers. It's all like, if you see the citation here, it's the year and the volume and the issue. So starting with clay mineralogy, again, this is whenever we talk about soil behavior, Jim Mitchell's book comes into our mind right away. So again, the clay mineralogy is basically covering different types of clays, their structure, and then when you compact them in a soil mass, it maybe constitutes to a fabric. So these are very important, what we call is underlying factors that affects the soil properties. So on the right side, you see the columns where you have properties like soil thixotrophy, which is again a time-dependent strength gain, which is given by Mitchell's paper. And if you look at down there, right side, there's a study done by Mitchell with the different types of samples prepared as molded and aged versus remolded, recompacted. So that clearly showed how the effect is actually was starting to show the differences in strengths based on the type of your sample preparation, which in turn accounts for the soil fabric. There's also papers by sensitivity, which is again linked with the cation exchange capacity and soil specific surface area. There are a lot of papers are listed there, including as recently as the Khorshidi paper. And then also the strength stability, there's again classic Mitchell's paper on that particular part. And then volumetric stability, which is again, clay mineralogy is well known for expansive soil. It's actually linked with the volume swell, shrink swell changes. That's something we've been working on, volumetric stability. And again, also other things like, aging, cementation, and then secondary consolidation. There are a lot of classic papers out there. And again, this is a part of the underlying of clay factors, how they're impacting it. In this slide, we talk about fabric. Fabric, basically, we're talking about both flocculated, dispersed, semi-flocculated to semi-dispersed. There are several methods, various papers that methods, including mercury intrusion porosimetry to different scattering, and now we see recent works on computerized tomography, and also some of them are covering with NMR methods. So there are a lot of papers I mentioned here, which are some of them are direct. Indirect, you see them like using wave propagation, image analyzers, and including discrete element modeling. And then on the right-hand side, you'll see these fabric effects and how this affects some of the properties of interest to geotechnical engineering. Like you can see soil fabric and also shear resistance, and then stress distribution and internal stability, as well as volume changes. Houston's paper is one of the first ones covered on this topic. And then you go into the pore size distribution related to permeability. There's again Wong and Hol's paper that covered this particular part, and then also soil creep part of that. And this slide actually covers some of the shear banding. Khalid Al-Shibli and Stein Stewart's work in 2000 actually talked about developing a shear banding in a fine Ottawa sand sample under triaxial condition. You can see the grid that is placed, and as the shearing is done, the shear band formation is clearly mentioned. And also, they showed the effect of various sandy soil properties like dry density, compaction density, or relative density, and then linking with the diameter of the particle, and then looking at the both loose and dense samples, so what is the banding, how it looks like. So this is one of the interesting studies. And on the right-hand side, you'll see some of the shear banding and how it's impacting various soil properties, including critical state conditions given by Finot's work, and also some of the anisotropic soils was given by Dr. Lade's work. And a lot of other folks are not only looking at the residual state parameters like Olson's and his group. So the Karami is actually looked at a discrete element model. If you see that figure on the right at the end, that clearly showed how the particle orientation and how it impacts the shear band formation. And now we are going into chemical stabilization. Again, this is still part of the soil behavior, because this is very important understanding soil behavior in terms of the reactions between soil and different additives that we add. So some of the cementitious or pozzolanic stabilizers, there are a lot of papers on this. One of the Jim Mitchell's papers in 1984, Tajagi lecture paper, talks about different stabilizations and also some issues like sulfate resistance. These are some of the important contributions by the journal. And then there are a lot of other interesting works done by dredged material. Grub has several papers on this topic, stabilizing dredged clays. And this is quite important these days in the coastal sediments and clayey sands. You see the Nilo Consoli's work, and in organic soils, there are several papers, including Teston paper. And again, these are mostly seen on the cementitious material. And of late, we see a lot of biopolymers. Like no-sulfonate is one of them. Indaratna has done some work on this. And biopolymers, there are several folks working on these different types of biopolymer additives. And then synthetic organic polymers is also of late is having a significant interest in the practice because of the relative quick in mixing them. So one thing when we looked at some of the papers published on the stabilizer, we looked at the different topics. Obviously, the cementitious materials, cement and lime and fly ash, initially they came out on the top. But one thing that is coming up faster very soon is the MICP. You see on that left side, that is also one of the, this figure is actually indicator of how many papers that are published in the JGGE. So MICP, if you ask the editorial board, they'll tell you there are a lot of papers nowadays we receive on the MICP work. So for that, I need to start with a little bit of intro of the Mitchell and Santmarino's paper on 2005. They talked about this biological or microbiological phenomena. We see on the right-hand side the figure that showed the different sizes going from nano to micro to milli size of the materials. And then you'll see on the same slide, they talked about different viruses and also some bacteria. And you can see the bacteria goes from micro to milli. So one of the things is mentioned here is this bacteria is mostly effectively, you can stabilize when you're dealing with slightly coarser silt to sandy soils and other areas. Again, there's a lot of research going on in finer materials also, but this is one thing has been a tremendous interest in the recent years on this topic. And you all know this paper again. Dizong has this paper. It's a 2006. Is probably one of the highly cited paper. And again, it showed first time MICP, the microbiological induced precipitation, can strengthen the sandy soils they used the urinalysis of Bacillus pasteurii, and they showed also not only shear strength, increase in stiffness. There are several folks working on this area that go from particulate level, like particle scale size level, to as high as the field scale demo. The particle size, I mentioned some of the works there. In the middle, you see some of the triaxial specimen size. Montoya's work is mentioned over there. And then now you started seeing them. This is going into practice also. So you see a lot more field scale demos that is happening right now. And I see some of the works from Arizona State University. They are doing some of the interesting works. And person is doing some of the field demo works. I'll talk about them a little bit later. There are a few other topics on the bio-geotechnical stabilization. They are known as EICP, which is more of an enzyme-induced carbonate precipitation. This is mostly coming from enzymes coming from jack bean or soybean or other types of materials. And they mix with it, and then they try to stabilize the soil. I see that a lot of interesting work is going on, and also some interesting applications, both in increasing pile foundation capacity, as well as increasing erosion resistant of a coarse sandy soils. These papers were published in the JGGE in the last, I would say, since 2013. And then on the right-hand side, you see more of a MIDP, again, microbially induced desaturation. The desaturation is happened due to nitrification, mostly nitrites converting into gas bubbles. So they create unsaturated environment that causes the material to have a more resistance to liquefaction. Again, I see some interesting work, including some of the work by Diane Moog in Portland area and the desaturation in real field conditions. Again, I see some of these topics probably reaching higher technology readiness level, where you'll probably seeing more and more field studies demonstrating how they can improve the performance. Also see some of the unsaturated soil work related to Banerjee, and then how it's helping with the liquefaction resistance. More details on this topic, you can see them in that recent JGGE talk by Ed Kabazanjian in 58th JGGE lectures. It's available probably on the YouTube also. Then I also want to mention about in situ soil characterization, the coming few slides. One area that's really a hard area is for US in the, I would say around late 90s or early, 2000s is again development of various cones, and that started with CPTU piezo cones. Again, some of the practice from Europe is kind of developed in the US also from several groups. Remember several folks like Tumai Schmertman and several folks like working in the West Coast, East Coast, they're working on it, and also Paul Main and David Frost, all of them. And then one area that's really hot is the Roman Heisius work with the vision cone that developed quite a bit. They used a cone with an optic eye. As you push into the ground, they are able to take pictures, and they're able to do a lot of interesting work. And I think it's mentioned also the Robertson's 1986 paper, one of the seismic cone, measuring extra parameter of shear wave velocity along with other 3 traditional parameters, really enhanced our capabilities of characterizing soils. So I list here a lot of soil. I'm not going to go into it, but a lot of this CPT interpretations works. Models for interpreting soil properties for clays or in situ soil characterization or sand characterization. There's so much work has been done. And also there's a lot of development on liquefaction. Thalia showed a lot of liquefaction assessment works by various methods by Ross Bullinger's and Idris's group. And again, there are a lot of things that came out on this particular topic from US. They're all published quite well in ASCE, JGGE. Also, I want to mention here a lot of interesting work by calibration chamber works done by at Purdue with Rudy, Salgado, and also Dr. Tumai's group at LSU. We had done quite a bit of work. Onbin Huang also did some work in the early 80s at Clarkson. Again, a lot of this work is mostly done at the calibration level. Then it went into the real practice. And also a lot of things are happening nowadays is more into how we can analyze with the limited data and then come up with the geostatistics and developing with the visualization. Of late, we're seeing a lot of this work, what you see on the right-hand side, that is by Santiago's paper. And again, this is the type of work is right now is expanding into site characterization. Some problematic soils, erodible soils is one of the areas, again, Dr. Bria, that A&M has done developing this EFA apparatus has been quite well used. And again, a lot of folks here worked on different internal erosion issues in the dams and different topics here. And also some other studies in the middle are looking at the soil filter criteria in cutting down these erosion issues. Again, I listed a few papers that have published in the ASCE JGGE. And also the one thing on the right-hand side, how do you model them? This is, again, it's of late has been interesting in how do you crack, developing the cracking during summer drying seasons, and then how it allows more erosion and suffusion processes. A lot of interesting papers are published in JGGE. They're all related to soil characterization. And then one thing is collapsible soil. The work's done by Sandy Houston, Dr. John Houston, and these works are very well mentioned in the ASCE journals. I can see the knowledge of collapsible soils, what causes this collapsing, and then also understanding the different methods using odometer versus triaxial and understanding the volume change and collapse potentials. And also there are some interesting works in the field. Rollins has done some mitigation methods on collapsible soils using different types of techniques. Again, these papers are published in 1994, Rollins and Rose's paper. This really looked at the collapsible soil. And of late, there's a lot of interest in this unsaturated soil mechanics since 60s. So some classic papers I mentioned from Blight 1967 to Fredland Morgenstern 77, and a lot of papers from, again, several groups. Again, I think there are also some interesting information on the soil properties, the stresses, and also understanding how the suctions in soils are changed with respect to environmental condition. And this has been of interest. I mentioned here several papers. Fredland has done tremendous amount of work on this measurement of volume mass relationships, and also a lot more and more work from Ning Lu and Dr. Liko's group working on different suction stress characteristic curve. Also, John Berg and McCartney is working on understanding the permeability changes in the unsaturated soil. So I listed several papers at the bottom on related to suction and soil water characteristic curve, and also linking them with the shear strength and moduli in the unsaturated conditions to some permeability properties on the right-hand side. And again, one area where I've been working is also with this unsaturated soil is understanding expansive soil. I had to mention several past works done with the by Houston's work, and also the work from Fredland, understanding this unsaturated soil properties, and then connecting them with the stabilizing deep mixing columns, and how do we understand the stabilized soils behave, or what happens to, or what changes that transpires into SWCC. This is helping quite a bit in converting into practice also. So again, I see a lot of interesting work going from theory to practice also. Like, there's a paper, 41st JGGE lecture by Fredland talked about some of the practice related information, and a lot of papers from Bill Lykos on the thermal conductivity to seepage analysis by Tim Stark and the group, and then other folks are working on plate load testing on unsaturated material. So there is a lot of interest going from unsaturated soil mechanics from lab level in field implementation, or understanding field issues a little bit better. This has been happening a lot in unsaturated. One last slide before I close is this is one area where, and Jim Mitchell has given his 20th JGGE lecture, he mentioned about this particular problem of this sulfate soil heaving. And again, they mentioned some of the, at that time, some parking lots in Kansas area to some areas in Las Vegas. There are a lot of work came after that. And some of the first few papers are published in JGGE, looked at the sulfate attack. And again, I mentioned after Jim's talk, Dale Hunter, he's a geologist from Nevada region. He talked about this issue. You see the picture on the left side, that is one of the highway in Nevada that was a few months old. It heaved very badly. So it went with a lot of understanding of soil behavior, soil chemistry, and what caused this heaving, and then how do we reduce it? And then there's a lot of interest work going on, and Dr. Rawlings from Army Corps of Engineers worked on the where the problems started actually on a treated soil basis. And then we've been working a lot on the sulfate soil. Because of a lot of work is happening in the last, I would say, 10 plus years, nowadays sulfate screening became a part of routine practice in in situ characterization. So again, this is one of the things that I feel journal has provided significant contribution, not only understanding from the research side, but also improving our practice. So with this, I would like to again acknowledge several folks, including Catherine, for inviting me to give this talk on this, and several colleagues from my geotech colleagues, both at TAMU and UTA and outside these schools also. And again, I want to thank my postdocs helping me with this slide deck. And with that, I close my presentation, and I invite Mo to give on the history.
Thank you, Anand. I'm going to share my screen. Thank you. I'd like to thank Brad, Matthew, and Dana for arranging the YouTube broadcast. Also like to thank Catherine. This session was her brainchild, and I thank you, Catherine, for seeing this all the way through to fruition. I'm delighted to welcome our colleagues who remain online for this presentation, and I'm honored to accompany you through 150 years history of your journal that informed and shaped the art and science of civil and geotechnical engineering. To provide context within the historical timeline, on some of the slides I have included historical structures and their completion dates. As we all know, the American Society of Civil Engineers was established in 1852. Please bear in mind that the public at that time wouldn't have had access to electricity, and means of communication, of course, were very limited. For example, as you know, the first message of the telegraph was transmitted in 1844. The transatlantic telegraph cable was laid in 1860. The phone, Alexander Graham Bell, invented the phone 1872, which incidentally was the year of the first transaction was published. First, we will acknowledge two visionary society presidents who recognized the importance of fostering knowledge sharing and safeguarding technical information for future generation. James P. Kirkwood, who was founding member of the American Society of Civil Engineers and the second president of the society. He championed the idea of creating transactions of ASCE for sharing information with basically absent members of the society who could not attend the annual and the various meetings across the country. He was then followed by William J. McAlpine, who emphasized the culture of intellectual growth. In his annual address that was published in the first volume of ASCE Transaction in 1872, I quote, he stated, the engineers who are to take over our place must combine degree of knowledge with the greatest skills and experience. End of quote. So from there, the motivation for establishing the transaction started, and volume 1 of transaction of ASCE was published in 1872 to serve as a repository for all civil engineering advancement, of course, including articles on soil mechanics and foundation. The transaction contained technical papers that were read to society members at various meetings. Volume 1 was published in 1872, but volumes 2 and 3 were published in 1874. So 2 volumes in 1874. And the papers were published only when the discussions on a given paper was completed. So the papers were published with their discussions. From that point on, 1 volume was published per year. While the transaction housed in-depth technical paper, it became apparent that there is a need to capture and quickly disseminate current activities, trend, news, and discussions that are specifically targeted toward practicing engineers. So 4 years after the publication of the first volume of the transactions, the proceedings of the American Society of Civil Engineers were established, and volume 1 was published. 10 issues of the proceeding were published per year, And I read that typically the month of July and August, the proceedings were not published. So as the technical field of civil engineering subdiscipline matured, the need for dedicated platform for each subdiscipline became evident. In 1906, the Soil Mechanics Committee of the ASCE was formed, which other, of course, committees, other civil engineering subdisciplines committee were formed as well, that made a significant step toward specialization. By 1924, the committee published its first standalone report highlighting the growing importance of soil mechanics in civil structures. In 1936, the first international congress, or what we refer to as conference, on soil mechanics and foundation engineering was held at Harvard University, where Terzaghi is the chair and Casagrande is involved in the organization making this conference happen. In the same year, the Soil Mechanics and Foundation Division was authorized by the ASCE, with Carlton S. Proctor as the chair. As you can see, the largest committee of there were 13 committees, I believe, as part of the committee of the Soil Mechanics and Foundation Division, and the largest committee was the one on earth dams. Perhaps the failure of St. Francis Dam that occurred in 1928 and claimed 431 lives, one of the worst in the history, might have had some influence on such interest. But you can see the list, and you can see this list of who's who. Basically, if you're interested in all the committees, you can look at the proceedings that were published in 1938. It will have these details, as you can see on the bottom left there. So the ASCE publication was basically taking charge of all the society publications. So for example, in 1948, it published 28 documents, 10 the monthly proceedings, 1 transactions, 12 civil engineering magazine, 4 manuals, and 1 yearbook. So a recognition emerged for the need for specialized publications per subdiscipline. So the transaction continued to encompass soil mechanics articles, but the call for dedicated subdiscipline publications grew louder compared to the all area inclusive transaction. So from there, the transaction in from there, the ASCE transitioned into journals starting 1956. So the first volume of the journals, volume 82, because remember the proceeding established in 1876. So the first volume, 1956, of the journal was the volume 82, and as you can notice, or I can notice at the bottom there, it still says the proceedings of the American Society of Civil Engineering, therefore the volume 82. The last volume of the general proceeding was volume 81, and the first volume of the journal was 82. The second issue of the Soil Mechanics Foundation Division volume included the committee on publication. So now we have a committee on publication specifically on soil mechanics and foundation division. And in this case, the committee was chaired by Ray Seed, including 9 members. And you can see this is a list of who's who, basically, as we can view it today. The journal started with quarterly issues, so 4 quarters per year, and then increased to 6 issues in 1959, 3 years later, and then it became annual issues in 1971. And at that point, T.H. Wu was the chair of the journal, of the publication committee, and the committee number grew to 19 members. No, I'm sorry, I misspoke there. That's not, yeah, 1971 when it became a monthly issue. That's THU with the chair, and the committee consisted of 19 members. 3 years later, the name of the journal was changed to the Journal of Geotechnical Engineering in 1974. The best account for the name change was described by Professor Roy Olson in his autobiography published as part of GSP honoring Roy Olson, GSP number 233. And it was argued that the title of Soil Mechanics Foundation Engineering does not encompass the field breadth, things like earthquake engineering or soil dynamics or rock mechanics and so forth. So ultimately, the ASCE members voted for geotechnical engineering. And basically, if you read the autobiography of Jim Olson, he said, Jim and I, that's Jim Mitchell, and I worked as subcommittee of two and came up with two names, Geotechnique and Geotechnical Engineering. As you all know, the name Geotechnical Engineering won that argument, I guess, or discussion. While the word geotechnical engineering was not used in our literature at the time, according to Brandl from Vienna University of Technology, in a paper published as part of the proceedings of the 15th European Conference on Soil Mechanics and Geotechnical Engineering in 2013, that word did appear the word geotechnical would appear in the final report of the Swedish State Railway Commission between 1914 and 1922. The publication committee at that point was chaired by Ernest Seeling from UMass Amherst, and as you can see, the committee in this the publication committee grew to 33, including the chair, with Ken Lee as the executive committee contact member. It's a contact member that serves on the publication committee in that case. Fast forward in 1980s, early 90s, with the circular and the introduction of RCRA and subtitle C's and D's, there was an emphasis on placed on the role of involvement of geotechnical engineering in environmental solving environmental problem, basically in problem related to groundwater remediation and protection of the environment. You know, the business of hazardous and radioactive waste disposal and solid waste disposal grew significantly during that time, and led by David Daniel, who's the editor of the journal at the time, support was garnered to update the name of the journal to the Journal of Geotechnical and Geoenvironmental Engineering to reflect the evolving nature of the field. In 1992, the executive committee of the Soil Mechanics and Foundation Division, or Geotechnical Engineering Division, supported the name change. Then in 1993, an editorial, in a joint editorial by David Daniel and Steve McTushin, I believe that's how you say it, presented the case for the more inclusive title of the journal, Geotechnical and Geoenvironmental, and published this joint editorial that you see on the right-hand side, emphasized the importance of collaboration between the geotechnical discipline and the environmental discipline. Therefore, the journal adopted its name change in January 1997, being the first issue to bear such title. With the first issue, January 1997, under the new name, the new editor-in-chief and the four editor also was a new system in that case that introduced, and that's what remains today as the operating governor system or governance system of the journal, if you will, in addition to editorial board member or the associate editor. In addition to the editor-in-chief and the four editors, the editorial board had more than 50, I believe I counted, if I count correctly, 51 what we called editorial board members, but what are now referred to are associate editors. So I finally end with the list of the past editors or editor-in-chiefs of the journal in the past 50 years. And as you can see now, we have seen the past. It's only befitting to acknowledge the giants who came before us and who have established the tradition of novelty, innovation, and excellence, and have laid the foundation for success. Like to also acknowledge Catherine O'Sullivan being the first female editor of our journal. Today, the journal remains at the forefront of the geotechnical and geoenvironmental engineering, and your journal continues to be a vital resource for researchers, practitioners, and students worldwide. Through your contributions as authors, reviewers, editors, we continue to push the boundaries of our field forward. I have immense faith that the journal will continue to thrive in the years to come, and I cannot wait to see what the future holds. Thank you.
Thank you so much, Mo, and thanks to all our speakers who've given fantastic contribution to give an idea of what's been achieved by this publication over the 150 volumes. So I'm going to invite some comments from the chat that are coming to me. I can see they are being typed through cyberspace. And just the first comment is from David Daniels, who said that to Rudy, it was a great talk and it was very appropriate to start by acknowledging Mitchell, Hooper, and Campanella in 1965, and thanks for putting that talk together. I'm not sure if there's any more. I think there's a couple of other questions coming in from the online audience. So there's a poll that's been carried out during the webinar, and it's asking what is people's favorite thing about the JGGE. So people were given the option to say, it gives me the opportunity to publish, I like reading the articles, or the association with the ASCE. And most people said all of the above. But the second highest ranking was giving the opportunity to publish and then reading the articles. So I think that at this point, we're going to wrap up. I thank the speakers really wholeheartedly for doing this repeat of the event that we had at the Geo-Congress, because now we're able to keep this synthesis you've done that I think is incredibly useful to the geotechnical engineering community on archive for others to access and appreciate the achievement of this journal. And again, I reiterate, I know this has been an enormous amount of work. You've had to go deep into papers and then come up and synthesize that analysis in just 15 minutes. And I really, really appreciate your voluntary time in doing that. And I think this is, going to be incredibly useful to the geotechnical engineering community as a whole. So thank you very much. And thank you to Brad and Dana for allowing us to take the ASCE resource to make this happen. And I'll pass over to you, Brad, perhaps to give the final couple of words.
That was pretty cool, guys. Thank you very much. And Mo, it was even though you had to move to the end and wrap up with the history, that was perfect. I can't believe how many of our EICs are still with us too. That was incredible when you put that slide up. So that is fantastic. A few of them were out there watching today. Roman just put a comment in the chat saying great job and he enjoyed it and he was here with us today. So it's fantastic. We really do thank you guys for all your hard work for the journal and for putting together these two sessions, the one in Vancouver and then the live stream today. We do want to say thanks. We would be remiss not to say thank you to all of the people who have worked on the journal over the years. Whether you were an editor-in-chief, whether you were an associate editor, whether you reviewed articles, whether you wrote an article, really any part of it, we would not have that journal without all of you. So we really, really appreciate, and the publication staff. I cannot forget that crew who sit in theory when there are people in the building one floor below where I'm at right now. It is such a huge team effort. I'm always a little amazed when you look at the list of reviewers for the year. It is a long list. It takes a lot of people to put together one issue, let alone 6, let alone 12 of JGGE. So we really appreciate it. So thanks again to all of you. Thanks to the people who watched today, stuck with us till the end. This was one of our longer live streams. So if you liked what you saw today, and you're here at the end, so you probably did, we do want you to click like, subscribe, and get notifications. We'll let you know every time we post something to the YouTube channel. In July, we have a couple of more things coming up. The first one is our next episode of our Geo Legends series. That'll be Liz Smith of Terracon, interviewed by Lucky Nagarajan. You can register to watch the premiere of that on our YouTube channel. That will be July 9th. And then July 11th, join us for a bonus Geostrata Extra where we talk with Teresa Laux, Archie Filschel, and Majid Kazabian on the I-95 reconstruction in Philadelphia last year. That'll be a big one. You can catch all of those, registration and info on all of those on our Eventbrite page, all of our upcoming events. We would love to see you there. So to all our presenters, thank you again today. Fantastic job. We loved having you. Our producer was Matt Roberts, and we will see everybody soon